I passed out problem set 3, okay? And there's going to be a holiday on April 4th, which is a Monday, so we won't have classes then. And then on Friday, April 7th, there will be only one hour lecture, okay, from 12:20 to 1:10. There won't be a lecture on April 7th from 1:10 to 2:20, okay? But, you know, I will make up for it later because there's going to be a total of 36 lectures anyway. And so, you know, whatever is canceled because of holidays or other reasons will come at the end, okay? Yeah, so I just passed out problem set 3. There are 5 problems. And so it's due in 3 weeks. Okay? Now, I'm still grading your problem set 1. I think I'll give it back to you on Friday, okay? So, yeah. Yeah, if you want to hand in problem set 2 today, that's fine, or you could hand it in on Friday, okay? Yeah. Okay, now, in order to build a model for equivariant cohomology, we need some differential geometry. So today I'm going to do the differential geometry that we need. Okay? It's called connections on a principal bundle. Okay? So how many of you have studied connections in differential geometry? Yeah. And have you done connections on like a manifold or connections on a principal bundle? Yeah, you've done connections on a principal bundle. Okay, good. Yeah, some of you have done it, some of you have not. So, you know, I will just go over it. All right? Okay, so I'm going to start with vector value forms. All right. Now, a differential form, right, it's the assignment of a k covector at each point. Okay, so let's just, but let's generalize a k covector to vector value k covectors. Now, a k covector on a vector space T is k linear alternating function. From Tk, which is Tk times to R. Okay, that's a k covector, and we can now generalize it to a vector valued k covector. Okay, so let V be a vector space, then a V valued k covector on T is a k linear alternating function from tk to v. Okay. Now, so by the universal property of the exterior power, lambda k t, okay? So we have a commutative diagram from tk to lambda kt, and then suppose we have an alternating k-linear map from tk to v, okay? Then there's a unique map, a unique linear map, f tilde from here to here, okay? So let's introduce some notation. So ak of tv, that's the v-valued k covectors and by the universal property of the exterior power, this is isomorphic to linear homomorphisms from lambda kt to v. Okay? And then from linear algebra, we have an isomorphism between Hom of WV and W dual tensor V. There's a canonical isomorphism. So this is isomorphic to lambda k t dual tensor with V. And there's also an isomorphism between the dual of lambda kv and lambda k of v dual. Okay? So these are facts from linear algebra. So this is isomorphic to lambda k v dual t dual tensor v. Okay? Let me see. Do we need finite dimensionality? For this one, maybe we do. All right, so I think to be on the safe side, let's assume that vector spaces are finite dimensional. Yeah, because that's all we only need finite dimensional vector spaces anyway. So, yeah. So, so here, let's put it on the top. So let's say we assume all vector spaces finite dimensional. Okay, and they are over R. Yeah. Now, so a V-valued K-form on a manifold M, and I'm always assuming C infinity manifolds. Okay? So a V-valued K-form on a manifold M assigns, is an assignment, is a function, actually, that assigns to each point P in M V-valued K collector in so a V-value K covector in this so lambda K of the cotangent space tensor V. And here it's P, all right? The cotangent space at P. And therefore, it is a section, i.e. it is a section of the bundle gamma K of the cotangent bundle tensor with V. Okay? So that's a V-value K form. And then it's C infinity if it's C infinity as a section. Okay. So the notation for the C infinity V-value K forms is this. These are the C infinity V-valued K forms. Okay. Now, if, say, E1 to En is a basis for V, then, and omega is a V-valued K form, okay? Then omega, when you apply it to K vectors, when you apply it to K vectors, okay, so let's say you have K vectors, V1 to Vk are K vectors at the point P, then so omega P applied to the K vectors it's in V, so it's going to be a linear combination of the basis elements, and that linear combination will depend on P and V1 to Vk. Okay, so it will be like this. And so therefore, see, omega is a linear combination of omega I E I, where the omega I are ordinary K forms. are R-valued K-forms on N. Okay? And yeah, so actually, once you fix a basis, then you can think of a vector-valued form as just a collection of ordinary R-value forms. Okay? And so this allows us to define the derivative, exterior derivative of a vector-value form. Okay? It will just be the exterior derivative of the coefficients times EI. Okay, so if omega is the sum of omega I EI, then d omega is just differentiate the coefficients. Okay, now it's very easy to show that this is independent of the basis. You know, if you choose a different basis, it differs from this one by a linear combination with constant coefficients. So the d with respect to the new basis is the same. So this definition is independent of the basis. Okay? Yeah.
So V is just a vector space?
Yeah, V is a finite dimensional vector space. Okay? And you choose a basis, then it's easy to calculate the exterior derivative. Okay? And then, now, if V is a V algebra, then we can define a bracket. So let's look at G-valued forms. Okay. So now let G be a finite dimensional V algebra. And omega is a G-valued K form, and tau is an L-valued, is a G-valued L form. Okay. Then, okay. Then we define the bracket of omega and tau to be a K plus L form. Okay, so it takes K plus L arguments. And we use the same definition as the wedge product. Okay? So it's minus 1. It's the sine of sigma over all KL shuffles. Sigma. So sigma is a permutation of 1 to K plus L. Okay? And then we take the bracket of V sigma 1 to V sigma K. Just a minute. The bracket of, okay, omega V sigma 1 to V sigma K. Yeah, so that gives you an element of G, and then tau of V sigma k plus 1 v sigma k plus L. Okay? All right, now this is at the point P. So this is at the point P, okay? And so that means, yeah, P is a point in N, and then V1 to Vk plus L are in the tangent space. Okay? In here, a KL shuffle, it just means, what does it mean, a KL shuffle? It means you don't take all the permutations, but only, right, those permutations in which these are in increasing order. Okay? So, KL shuffle it means that sigma 1 is less than sigma 2 is less than sigma k, and then sigma k plus 1 is less than sigma k plus 2 is less than sigma k plus L. Okay? So it's exactly the same definition as the wedge product, except instead of the product of two real numbers, now you have the bracket of two elements of the Lie algebra. Okay? So that's the bracket. Okay? Yeah. And so let's write. Okay, good, thank you. Yeah. Okay, now I'm going to write down a number of properties of G-valued forms. Okay? So these are all properties that follow kind of directly from the definition. Proposition, if x1 to xn is a basis for the Lie algebra, then omega is the sum of omega I xi, and tau is the sum of tau j xj. Then omega bracket tau is the sum of omega I wedge tau j bracket bracket xi, xj. Okay? That's the first property. And then okay, and then now if you interchange the two, okay. Now what is the sign here? Normally, if you interchange a K form and an L form, right, then the sign is -1 to the KL, to the product of the two, right? But here, what do you think the sign should be? I mean,
it's KL plus 1 because there's...
yeah, you see, if you interchange omega and tau, so these two will get interchanged. So you'll get -1 to the degree of omega times the degree of tau. However, these two will be interchanged also. And that will introduce an extra sign. So it's going to be -1 to the degree of tau, or degree of omega times degree of tau plus 1. Okay? There's an extra -1 that comes from the bracket. Okay? And then if you take the exterior derivative of omega tau, oh, sorry. Yeah. No. Yeah. So you differentiate this, right? So you would differentiate the first factor, and that is going to be d omega tau, and then plus -1 to the degree of omega, and then you differentiate this guy, so that will give you omega d tau. Okay? So it's the same formula as if you had the wedge product. All right? So these are properties of a Lie algebra valued form. Now, your Lie algebra might be G, L, and R. So these are the n by n matrices. Okay? Now, if you have forms with values in the matrices, then in addition to the Lie bracket, you have another operation. Right? You can multiply square matrices. So GLNR has two multiplications. The Lie bracket and matrix product. Okay, so let's see. Now a basis for GL and R is EIJ, where okay, so it's EIJ for IJ from 1 to n, where EIJ is the n by n matrix with 1 in the IJ position and 0 every where else? Okay. All right. Now, so if you know how to multiply these EIJs, then you can multiply any two matrices. Okay, so let's see. So let's say you want to multiply EIJ times EKL. Yeah, so what do you get? I mean, you have two matrices. So EIJ, it has a 1 here. And then EKL, let's see, has a 1. Okay, so in K and L. Now, so you see that, okay, when you do your multiplication, you're going to get 0 everywhere except from the ith row and the lth column, okay? So you could get a 1 there. And that 1, when would that 1 not disappear? When j is equal to k, they will line up, okay? So this will be delta jk. Yeah, so that's the formula. If j is equal to k, you get a 1, and then you get EIL. Otherwise, you get 0, okay? So that's the formula. Yeah. I'm going to put it in a box. EIJ times EKL is delta jk EIL. Okay, so delta jk is the Kronecker delta. Delta jk is 1 if j is equal to k, and 0 if j is not equal to k. Okay, we have that formula. So for matrix, for GLNR value forms, you have two products. You have the Lie bracket, and you have a wedge product. So definition, if omega is the sum of omega ij, eij, and tau is the sum of tau kl, ekl, then we define the wedge product of omega and tau to be the sum of omega ij wedge tau kl, eij times ekl, okay, and then eij ekl is this. Okay, so it's non-zero only if j equals k. So this will be omega I k, which tau k l e I l. Okay, so that's the definition of the wedge product. Okay, now Now we have two kinds of products. And there's a relation between them. So here's the proposition. If omega and tau are differential forms on M with values in G, L, and R, then the Lie bracket is related to the wedge product by omega wedge tau minus 1 to the degree of omega degree of tau wedge omega. Okay. So we have this formula. So normally the wedge product is just of x and y is xy minus yx, but here these are graded things, so when you interchange them you have this extra sign, okay? And again, this just follows from writing everything out in terms of bases, so it's pretty straightforward. So as a corollary, let's see, what is the bracket of omega omega? Yeah, so it depends on this sign, right? So the bracket of omega omega, let's see, if the degree of omega is even, this will be 1, and then you get 0. So this will be 0 if the degree of omega is even. But if the degree of omega is odd, this will be a minus 1, so this will be a plus 1, so then you'll get 2 omega wedge omega if the degree of omega is odd. All right, yeah. Okay, so that's all I want to say about vector value forms, and we still have 10 minutes. Okay, so now now I want to look at principal bundles. Let's see, well, not principal bundle, just a G space where G acts on the right, okay? So suppose a Lie group G acts on manifold P on the right. then for an element in the Lie algebra of G, we can define the fundamental vector field. So at the point P, and now we can translate it on the right by G. So RG lower star, okay, of this. And the proposition is that this is equal to, now it's going to be a vertical vector at PG. Well, it'll be a vector at PG, and it's going to be associated to add G inverse times A. Okay? So here add is the adjoint representation. Okay, so this is going to be a very important formula, and so I'm going to put it in a box. Okay. So now, we denote by CG conjugation by G. So CG from G to G is conjugation by G, and that means CG of X is G XG inverse. Okay? And so the differential CG star will go from the tangent space at the identity to the tangent space at the identity, because the identity goes to the identity. Okay? So CG star, and this is the Lie algebra. And this is the definition of add, the adjoint representation, add G. Okay? So add G takes an element of the Lie algebra to an element of the Lie algebra. This is the definition of add G. Okay? All right? So now let's prove this formula. Now, see, I have another way of getting the fundamental vector field, right? Let JP be the map that takes G to P dot G. Then to calculate the differential of JP, I take a curve with initial vector A, so that's e to the TA, and then I take the image of that curve and then differentiate with respect to t. So this is d dt at t equal to 0 of p e to the TA. And that's a definition of A bar p. Okay, now suppose we right translate, so right translate by G, okay? Then, so I first, let me see. Yeah, so I first have px, and then I right translate by g. So I get pxg, and that's equal to pg dot g inverse xg. Okay? So that's pg dot conjugation by g inverse. Apply to x. No, just a minute. Let me see. This is that's right, yeah. So this is an element of G, right? X is an element of G. And this is JPG applied to CG inverse X. And so so therefore, and I can write this as JPG composed with CG inverse applied to X, okay? So what I have shown is that if I right translate JP by RG, I get JPG composed with conjugation by G inverse. And so if I take the differential, so that's the chain rule. By the chain rule, when I take the differential, I get RG lower star, JP lower star is equal to JPG lower star, CG inverse lower star. Okay? And then I apply this to an element of the Lie algebra A. And so this will be RG lower star of A bar P, and this will be JPG lower star of the differential of conjugation is at G inverse A, and so it is at G inverse A, the fundamental vector field associated to that element of the Lie algebra at PG. Okay? And so that's the formula that we wanted to prove. Okay? Okay. So I'm going to stop here, and then in the next hour, I will discuss connections and curvature on a principal bundle. Okay? So let's take a break for 10 minutes. Yeah. Okay. And some of you came late, so did you get this problem set? No, did you all get the problem set? Yeah.